We're gonna do decoders now. Basic usage of a decoder is to decode its input and give specific output corresponding to it. In general, the decoder has n inputs and 2 to the power n outputs to cover all the input combinations. So here the relationship between the inputs and output is n equals to 2 to the power n. So these are your inputs right here, and these are going to be, this n is going to be, this whole thing is going to be your output right here. Okay, so notice we got two inputs right here, A and B, and we got 4 outputs here, out 3, out 2, out 1, and out 0. So out 0, out 1, 2, out 3. So decoder does exactly opposite of the encoder, and we have I have one example at the very end that should explain you why are we using decoder. Actually two examples that we are going to do today. So we're using a 2x4. This says 2 inputs and the 4 outputs. So I have a truth table here. Again, we are going to generate this truth table, and then using that truth table we are going to come up with expressions for each of the output, and then we're going to do the implementation. So for the 2 inputs we have 4 possible combinations. The range goes from 0 to 3. Okay. If the input is 0 0, what should be the outputs here? Output 0, 1, 2, and 3. You apply the same logic that you did in encoders. Okay, you look at the binary code and you come up with a decimal number, and that line would be high, correct? In this case, you're going to do the same thing. 0 0 makes a code of what? 0, right? So out 0 is going to be high, and rest of the others are going to be low. Okay, so it's going to throw one output at a time. Similarly, 0 1 makes a code of 1, so output 1 is going to be high, rest of the other are going to be 0. 1 0 out, this is going to be high, the rest of the 0, and 1 1 out 3 is going to be high, rest of the other outputs are going to be 0. If we come up with expressions for the outputs here, so what is the expression for out not here? Come on guys. I know we are coming from a break, but this is pretty simple, right? So we look at this column, right? How many minterms do we got? We only have one minterm. What would be the expression? A bar, B bar, correct, thank you. Okay, what about out 1? A bar B, out 2 is going to be A B bar, and then out 3 is going to be A B, okay? So say these are your out 0, out 1, out 2, and out 3. We got our inputs here, A and B. So we basically need 4 AND gates here, correct? Okay. So out 0 is actually A bar, B bar. So say I'm going to use bubble here instead of inverter. A bar. This is B bar. Okay. Out 1 is A bar B. Okay, out 1 is A bar B. I have this B right here, so I'll just, okay, and this is your A, Okay, and it has to have a bubble because the out one is A bar B. This is A bar B right here. Out 2 is A B bar. So B goes right here. Got this node right here, and then A. So this is A B bar. And out 3 is A B. This is B. And this is A. So this makes AB. Okay. So this makes your 2x4 decoder. So again, just like the encoder, these are combinational circuits, and this is what goes inside a 2x4 decoder. If we have a decoder that has 4 inputs, how many outputs we would have? 4 inputs, how many outputs? 16. To the power 4 is 16. Okay. All right. Let's move on to our next. Actually, we are going to create a Verilog code for it here now. Okay. Okay. All right. I have already done some commenting here. So we'll start off with the module name. So we say module space, I'll just say decoder. Notice I got my inputs in the logic diagram in the implementation in green, and those are A and B. And then I got my outputs in red, those wires, which are out 1, out not, out 2, and out 3. So I'll just create an array for it. So I'll just say out. Okay, semicolon. Port definitions input A comma B semicolon output. Let's declaring those output as an array. So we got 3 colon 0 D here. Okay, and then assign D0 D1 D2 D3. I noticed that in the supporting material that I gave you, I only have 3 assigned, so you can use a semicolon. Okay. So D0, what is going to be the expression for D0? It was A bar B bar. So A bar ending with B bar, correct? D1 was A bar B, A bar ending with B. Right? D2 is A B bar, A ending with, so this is A B bar. And D3 equals to AB, so A ending with B. Okay, so this is AB. Okay, and we say end module. Okay, so this is how the code is going to be for the decoder. Okay, shall we move, guys, to the next example? Yes. Say it again. So these are the outs 0, 1, 2, and 3. Okay, all right. And I'll also make the change over here. Actually, not over here, but over here. I'll make this D. Okay, because this and this has to match. Okay, all right. I was initially going to use out, but then I thought I might not have enough space, so I'll just make it D. So, but yeah, that was a good point. Okay, all right. Moving on to example number 2. The good thing about decoder is you can actually implement any truth table using decoder. You don't have to, there will be some applications where there's going to be a huge combinational circuit, but instead of making that combinational circuit, you can actually use decoder, and it is so simple. So this next example is going to explain that, how you can do that. So it's the same example that we did a few lectures ago. It's a full adder implementation. So you got your inputs A, B, C, and then sum and carry. I went ahead and filled those values in the truth table for sum and carry. Let's get the minterms here. So we got your inputs here, C, and those are for sum 1, 2, 4, and 7. Okay. And then here I have, for carry I got 0. So I got 3, 5, 6, and 7. Okay. What kind of a decoder we have to use in order to implement this truth table? Remember, we have 3 inputs A, B, C, and we got 8 outputs, right? Each for sum and carry. So what kind of a decoder we would need here? Come on. Has to be a 3 by 8 decoder, correct? Okay. It has to be a 3 by 8 decoder. Okay. Again, decoders could be active high or active low. They also have this enabled. So say this is active high, so this is actually just connected to VCC. Okay. So when 1 it's enabled, 1 would mean 5 volt here, or whatever the voltage is here. So our inputs here are going to be A, B, and C. And how do we implement a truth table using decoder? We actually OR the terms. Okay, so notice you got OR, 2 OR gates. Okay, one would be for the sum and one would be for the carry. Okay, what are the minterms that go into sum? Those are 1, 2, 4, 7. M0, M1, M2, M3, M4, M5, M6, M7. So these are all the outputs. So 1, 2, 4, and 7. So 1 goes here, 2 goes here, 4 goes here, and then 7 goes here also. Okay, so I got 1, 2, 4, and 7. Okay, all right. For the carry, I got 3, 5, 6, and 7. This is 7 right here. This is 6 here. This is 5 here. And then 3 is over here. Okay, so I got 3 here, 5 here, 6 here, and 7 here. Okay, remember when we did the full adder before, we actually did the K-map, came up with an expression for sum and carry, and then drew the combinational circuit. Well, instead of doing that, you can actually do 3 by 8 decoder, and you don't have to worry about those combinational gates. We can verify our logic here. Say our A, B, and C all are set to 1. So you got 1 here, and 1 here, and 1 here. What would be the output here? 111 makes a binary code of what number? 7, right? This right here means this M7 is going to be high. What the other outputs are going to be 0. Okay, so this will be high. Rest of the others will be 0, right? And notice here you got 7 going into both of these, correct? So this is going to be 1, rest of them all are 0s. This is going to be 1, rest of them are all 0s, correct? So the any of the input is high going into OR gate, output is going to be high, and that's what we were expecting when we have 3 bits all set to 1 and we are adding them. Sum is going to be 1, carry is going to be 1, which we get over here as also. Okay, so you may get a problem in homework or in exam, implement some application or function or truth table using decoder. This is how you would do it. Basically just choose the configuration of the decoder. In this case we had 3 inputs and 8 outputs, so we went with the 3x8 decoder, and you're just ORing the outputs, okay, the min terms. Okay, any question, guys? Let's move on to our next example. Okay, our next example is a 7-segment display decoder. This week you guys will be doing lab number 3, right? And you will be actually be using 7-segment decoder. So those of you who have already started looking at the pre-lab or the documentation for the Basis 3 board, the LED 7 segments on your Basis 3 board are active low, correct? Means the segments are going to be on when you apply a 0 logic to it. And because you're going to be practicing active 0 logic, low level logic on Basis 3 board, I thought in the class we do a reverse of it. Okay, so this is a 7-segment display. However, it has the active high logic or property. Okay, so this would mean if B3, B2, B1 and B0, they are all set to 0, we want to display, it makes a binary code of 0. We want to display 0 on our 7 segment. So which of these segments needs to be high or turn on? I should say turn on. In order to display 0, all the segment needs to be on except for G, correct? Right? So G is going to be 0 and the rest of the other segments are going to be 1. Okay? This is your A, this is your B, this is your C, D, E, F and G. Many 7-segment these days have this decimal point also, which is referred to as H segment. Okay. Okay, what would be the output for 0, 0, 0, 1? And because we have 7 segments here, so these are our 7 outputs right here. A, B, C, D, E, F, G. These are the 7 outputs. What would be the output for 0, 0, 0, 1? Here, folks. In order to display 1, which segments needs to be turned on? B and C, right? Or E? F and E. Oh, okay, yeah. So we got 2 options here, right? You can either do FE or you can do either do BC. We usually do BC for it. Okay, we usually do BC. Nobody said that to me ever, so that's a good. We got some innovative students here also, some creative. So okay, all right. Even I never thought so. Okay, all right. I actually went ahead and pre-filled some of the combinations so we can spend more time on the examples. 0, 1, 0 makes a code of 5. So what segments needs to be turned on for 5? Okay, F, G, C, and D also? 0, 0. Okay, all right. What about 7? A, B, C, 1, right? A, B, C, 1, rest of them are zeros. 1, 0, 0 makes a binary code of 8, so that means all the segments are going to be on, right? So that means 1. Remember 1 is on, okay? Because it's active high. Okay. Let's do the K-map. Did not want to do for all of this. Yes. For which combination? This right here? Okay. So we need F, G, C, and B. F, G, C, and B. Correct? Yeah. Is there any rest of the other combination looks okay? 0 0 1 1. So we need A B G C D E. A B G C. Yeah, that one looks okay. 2 would be A B G D. A B G E D. Yeah, this looks okay. This looks okay. This looks okay. 1106 would be A F G C E D. A F G C E D. This looks okay. And 9, so A F G B, A F G B, and then C. C looks okay. All right, good. Shall we move on? Good. Okay. All right. Let's do the K-map, and we are only doing it for A and B. Remember. So we look at these columns right here, and we look at the minterms. Notice this is only went from 0 to 9, so that means it's a BCD, correct? So which would mean what would happen to 10, 11, 12, 13, 14, and 15? Those would be treated as don't cares here, okay? All right. So I can just do the don't cares here. 10, 11, 12, 13, 14, 15. Similarly, I can do the don't cares over here also. Okay. Now let's look at the minterms for the A. 0 is 1, 2 is 1, 3 is 1, 5 is 1, 6 is 1, 7 is 1, 8 is 1, and 9 is 1. Okay, all right, folks. How would you? 6 is 1 too, yeah. 110 is 1, correct? Yeah. All right. Does the minterm looks okay in my K-map? Looks like, okay. All right, what would you do? I'm pretty sure most of you are thinking the group of 8 at the bottom, right? So that's the biggest one, right? We can get this right here. Okay. Does anyone think we can get another group of 8? The 2 columns on the very right? Okay. What else? 4 corners? Okay. We got one minterm that is still not covered yet. How can we cover that? Remember, our goal is to go for a biggest size of rectangle. Yes. 5, 7, 13, 15. Okay. All right. Sweet. Awesome. Thank you. Okay. Let's get the expression here. So this red one at the bottom, the common here is B3 plus this one common is B1 plus the one in the middle common here is B2 and common here is B0 plus this chord on the edges sides, the common here so B2 bar and the common here B0 bar. Okay, so this is the expression for A. Okay, let's do it. Let's now do it for B. I'm gonna look at this column right here. So 0 is 1, 1 is 1, 2 is 1, 3 is 1, 4 is 1, 7 is 1, 8 is 1, and 9 is 1. Okay, how would you do this one right here? Again, we can go for this group of 8 here, correct? Okay, top row. How many of you think that we can go with the top row? Yes. Yes, we can. You remember we can wrap it around and they will be considered as adjacent ones. Okay, what else, folks? We have 2 min terms which are still not covered. Yes. 3, 7, 15 and 11. Great, fantastic. So basically 2 cards right here. And then this one right here. Okay, let's get the expression. This bottom card was B3. Sorry, the group of 8. And then we had this top row and the bottom row. The common is B2 bar. Plus this first column is B1 bar B0 bar. Plus, and then this column, the third one, is B1 B0. Okay. Okay. Remember, you're going to have to do this for A, B, C, D, E, F, G for pre-lab, but you can use Logisim. So the tutorial that I made for you just runs through how to drive a logic expression for all the segments from A to G using Logisim. So that will be a faster way of doing it. You don't have to do it by hand, but I just wanted to do at least 2 of them. Okay, all right. Let's move to the implementation part. So we use inputs as B0, B1, B2, B3. So we got B0 here, B1, B2, and B3. Okay. And then our outputs are going to be A, B, C, D, E, F, and G. And say this is for decimal point here. Okay. And we know if I have B3 0, B2 is 1, B1 is 1, B0 is 1. We know our A segment is going to be high, this right here. Okay. Our B segment, which is here, is going to be high. And which other segment is going to be high? C. Okay. This is going to be enable here. Say it's active high, so connected to VCC. Okay. So this is how the 7 segments work on FPGA or in general. I also have this interesting example here at the bottom. Say you go to an ATM machine and you see that keypad and you type in your code and it does things for you. How is that working? So say you go and you press 7. Okay. And again, because we got numbers from 0 to 9, so they are utilizing BCD segment that goes from 0 to 9, and the input goes through the encoder. Okay. So this is going to be an array, some number. So step by step, what happens when you press 7, how it appears on the 7 segment? Well, you input 7 of 74147 IC is activated, and say this is a active low chip. So is activated by low. Okay. What would be the output over here? What is the output over here at the encoder? It's an active low. What is the binary code of 7? 111. How many bits are we going to have here? It's a BCD segment, so we're going to have 4, right? So that would be 0111, and because it's active low, so the output is going to be 1000, correct? Right? So here we get 1000, okay? 1000 is then sent to the inverter. So what would be the output of the inverter? 0111, right? So using inverter, we get the original value for 7. Okay, all right. 0111 going into 7-segment decoder is going to do what? 0111 going into decoder is going to do exactly what we did over here, right? 0111 is going to light up A, B, and C. A, B, and C here. Okay, so segments A, A, B, and C lights up. Okay, here our decoder was active high. How I would know that? Or say if you know encoder was active low, decoder was active high, why were they using inverter? Come on, guys. So this truth table that we have is for active high, correct? If I change the wording here, active high to active low, all these values are going to change, right? Correct? Similarly, because this decoder was active high, I had to get the original form of 7, which is 0111, so I had to use the inverter in between so I can get 0111. Because this was active high. If this was active low, I probably didn't need the inverter over here. Okay, make sense, guys? Okay, let's move to our this example right here. Often you use smaller standard functional blocks to make a larger element and block. Okay, usually we try to use the smaller blocks as we can, and then we can put them together to make larger one. For example, this is an example on 4x16 decoders. So believe it or not, you can actually make 4x16 decoder by using 2 3x8 decoders. And how we would do that? So say you got your inputs here, which are A0, A1, A2. In enable, we will consider that as an input here. Okay, so we will say this is our A3. And similarly here we have our A0, A1, A2, and A3. Okay, now what is the trick behind it? Well, the trick is I'm actually going to use an inverter here, okay, and feed it to the enable. And what is the input going into the enable? It's actually this enable right here. Okay, so which means what? If this enable is 1, this enable is what? 0. They are always going to be complement of each other, right? So say if this is my top module and this is my bottom module, there can only be one module working at one time, correct? Everybody understand that part, right? Now these are going to be my outputs. So say this is out 0, out 1, and then so on. This is our out 7, this is our out 8, out 9, and they go all the way to out 15. So notice now we have 4 inputs and we have 16 outputs, and we want to verify whether this is working or not. Remember again, A3, if you look at this A3 column right here, for the half part, it's 0, correct? If A3 is 0, then this A3 is going to be 1 here, right? So for the first 8 combinations, this is going to be active and this is going to be off. And for the next 8 combinations, when A3 is all ones, this is going to be off and this is going to be on, correct? So let's try one combination here. Say you have A0 is 1, A1 is 1, this is A2 is 1, A0 is 1, A1 is 1, A2 is 1, and A3 is 1 also. Okay, so this A3 will be what? 0 here, right? If this enable bit is set to 0, that means this is not functioning, so all the bits are going to be what? 0, right? Basically. Here enable is 1, A0, A1, A2 are all set to high. What would be the output here? Yes. Output 15 is going to be high, right? Because what we know is output 15, decoder understands as 7. Right? 3 makes a code of 7, right? Which we are declaring as output 15. So we as, you as a designer knows that, but what users see is only this part, right? The user doesn't see that we are actually using 2 3x8 decoder to make a 4x16. Okay, so that's a trick behind it. And when we go into flip-flop, we'll do more of this, how we can make complicated circuit by just using these kind of techniques.